Good evening. We were looking at three-phase induction motors principle of operation in the last class. What we said was that the stator has a three-phase space distributed winding. It is supplied with three-phase time distributed currents to generate a revolving magnetic field in the intervening air gap between the stator and rotor. Now what happens is the rotor conductors, which are short circuited, and stationary, because initially when you start, the rotor is not going to be rotating, so it will be stationary. They visualize revolving d phi by dt, that is rate of change of flux, when they are placed at the outer periphery of the rotor. So it is actually facing the air gap, so which is in the air gap. So what happens is this causes an induced EMF in the rotor conductors, which is proportional to the flux magnitude as well as omega s minus omega r, where omega s is the speed at which the revolving magnetic field is rotating and omega r is the actual speed of the rotor. Now, because the rotor is short circuited, there is a circulating current. So there is going to be a three-phase circulating current. This creates a revolving rotor field or rotor flux. So let me call this as psi r. And whatever is the original revolving magnetic field, let me call that as psi s. So now what happens is the interaction between psi r and psi s creates an electromagnetic torque that opposes the root cause for torque production. So the root cause for torque production is omega s minus omega r. We already said that if omega s minus omega r had been 0, there will not be any induced EMF because it would not have seen even a rate of change of flux. So, as per Lenz's law, TE will try to accelerate the rotor in the same direction as that of omega s. So this is what is causing the rotor to rotate in the same direction as that of the revolving magnetic field. If rotor starts or reaches omega s, then the rotor conductors will not visualize any change in flux. So no induced EMF in rotor conductors. So no torque production. So omega r will fall. The moment omega r becomes less than omega s, there will be induced EMF and torque production. So when the load on the shaft is minimal, the rotor will rotate at a speed close to omega s. At this point, the induced EMF and current in the rotor conductors will be really small because this is proportional to omega S minus omega R. So the current and torque will be very, very small because omega S minus omega R is small, and this is sufficient to sustain the rotation. With a small amount of electromagnetic torque, with a very small amount of electromagnetic torque. So when you load the shaft more and more, you are going to see that the difference between omega S and omega R increases. That is, the rotor is going to lose some speed. So the induced EMF will be definitely larger. The current will be larger. So electromagnetic torque will be larger. So when you load the motor more and more, you will need more torque. And that is automatically balanced by higher torque production, which is resulting from a reduction in the rotor velocity. That's what happens in induction motor. Okay. So let us try to quantify exactly how the torque production can be, put in the form of an equation. That's what we are going to look at. So let us look at the torque production mechanism from mathematical point of view. So let us say if I am looking at an induction motor, I said that there are three-phase conductors in the stator. And rotor, although it can be in the form of squirrel cage rotor, that can also be converted into equivalent three-phase form. So three-phase conductors are present in both stator and rotor. But only thing I can say is the rotor conductors are short circuited. Rotor conductors are short circuited. And there is basically an air gap between the stator conductor and rotor conductor. That is going to cause whatever is the flux that is created by the stator, that is not going to be completely linking, or it is not going to completely be utilized to induce an EMF in the rotor. So some of it is going to be wasted because it has to pass through an air gap. So the whatever is the quantity of flux that is wasted, it is not going to link with both the members, that is stator and rotor conductors. That is known as leakage. So the three-phase conductors which are corresponding to the stator as well as rotor, if I just look at them from a per phase point of view, only one phase at a time, they behave like a transformer. So let us say I am going to have this is the stator conductor which is sitting here, and this is going to be the rotor conductor which is sitting on the secondary side. So let me call this as primary or stator and secondary or rotor. So if I have an induced EMF of E1 or applied voltage of V1, from which let us say there will be some inherent resistance in the stator conductor, although it is made up of copper or aluminum or whatever, it will have some resistance value. And as I just mentioned, there will be some amount of flux which is not linking with both stator and rotor. So whatever is the leakage, I am calling that as X1. And what I am applying per phase, I'm calling that as V1. So V1 is the voltage that I'm applying here. And after the drop that takes place in the resistance and leakage reactance, whatever is left over here, I'm calling that as E1. Now, if I have N1 turns here and N2 turns here, I'm going to have E2 as the induced EMF, especially when the rotor is in standstill condition. And definitely the rotor conductors will also have their own resistance, and we are going to have some leakage. Definitely all the flux that is produced in the rotor circuit is not going to link with the stator. So let me call this as R2 and this as X2, and this is short circuit. So this is the equivalent circuit of the induction motor per phase when the rotor is in standstill condition. That means it is not rotating at all. When it is in standstill condition, this is what is happening. Okay. So once it starts rotating, the rotor starts rotating, we said that d phi by dt, that is what is going to give me E2 in a way, because whatever is the rate of change of flux that is visualized by the rotor conductors, that is going to give me E2. But if the speed of the rotor increases, then I'm going to have this particular dt value, that is the rate of change visualized by the rotor, that is not going to really be that fast. It is not going to see the change so fast. So I'm going to have d phi remaining the same, but dt, if I try to look at it, that is going to increase. So because of which E2 will decrease. So omega S minus omega R plays a vital role in deciding how much is the induced EMF. We have a specific quantity called slip in induction motor, which we define as omega S minus omega R divided by omega S. So this slip actually decides indirectly what is the magnitude of this induced EMF E2. And not only that, if the rate of change is decreasing, if I'm not able to see as much rate of change as I was seeing, the frequency of the induced EMF. So F2 is the frequency of rotor induced EMF. Even that is going to decrease. The frequency will decrease, the magnitude will also decrease. So I should say both F2 and E2 magnitude will go down if slip decreases. So at zero speed, when I'm talking about zero speed, slip is equal to 1. Slip S equal to 1 at omega R equal to 0, because omega S divided by omega S. Whereas as omega R increases, slip will decrease. So rotor induced EMF and the frequency both will become S times E2, where E2 was the EMF at standstill condition. When I had E2 as the induced EMF as in standstill condition, S times E2 becomes the induced EMF at any other speed omega R. And S can be calculated based on this particular expression. So we can say the equivalent circuit, especially whatever I have drawn here, I should be able to replace this by S times E2 and this as S times X2. That is now the equivalent circuit what I see for the induction motor on a per phase basis when the speed is non-zero. Speed of the rotor is non-zero. So here, if I say that the current that is flowing here is some I2, I can write here I2 equal to SE2 divided by R2 plus JSX2. So from which I can say I would, this is very specifically the current at slip frequency, which is actually F2. This current is going to be at a frequency, SE2 is also at a frequency of F2. Where F2 equal to S times F1. If I may call this frequency here as F1, the frequency of the induced EMF in the rotor is going to be F2, which is also S times F1. So I can write the same equation I2 equal to E2 divided by R2 by S plus JX2. Now please note, originally whatever we have written as equation, we have just divided the denominator as well as numerator by S. Nothing else we have done. But here we said the rotor frequency is the frequency of this current. Whereas here, E2 is the standstill induced EMF in the rotor circuit, which is also at the frequency of F1. So we are trying to convert this equivalent circuit of the rotor such that the frequency would become same as that of stator. That's what we have done by modifying this equation in this form. Now, we can draw the equivalent circuit somewhat like this. I'm going to have R1, I'm going to have X1, and I have got E1, and I have got V1 being applied here. And on the other side, I am going to have S times E2, which I have converted into E2 now. And I'm going to have R2 divided by S. And slip is a variable quantity, so I should show this resistance as a variable quantity. And the leakage reactance still remains as X2, which was the value even at zero speed for the rotor, and this is short circuit. Now what I have got here is I2, and I2 is going to be the rotor current, which is equal to E2 divided by R2 divided by S plus JX2. Now, if I am looking at what is the kind of power dissipation that takes place in this fictitious resistance? The actual resistance is only R2, but R2 by S I have specified as the resistance with some manipulation that I have done here. So I should say power input to the rotor circuit, that is going to be I2 square R2 divided by S. This is per phase. But I know for sure that the actual dissipation in the rotor resistance that is going to be I2 square R2. So I can say I can see the rotor rotating clearly. So there should be some amount of input power to the rotor circuit which has been converted into mechanical power. So I can say mechanical power output from the rotor. That should be equal to power input minus resistance loss. So that should be equal to I2 square R2 divided by S minus I2 square R2. So I can write this as I2 square R2 multiplied by 1 minus S divided by S. So this is per phase mechanical power output. Now, because this is functioning exactly like a transformer, I should be able to transfer this resistance and this inductance to the other side. So if I may call this number of turns as N1 and this as N2, I can very well say this resistance transferred to the other side, that is from the secondary side to the primary side, that is going to be R2 multiplied by N1 divided by N2 the whole square. The same way, X2 dash, if I transfer this leakage reactance to the other side, then I should say X2 dash equal to X2 original value on the secondary side multiplied by N1 divided by N2 the whole square. Okay. So I should be able to combine these two. This is also at F1. This is also now at F1 because I have transferred the slip term by dividing S times E2 by S itself. So I have made this also stator frequency. This also is stator frequency. So all I need to do is to use the turns ratio and combine this equivalent circuit. So I can draw the equivalent circuit, approximate equivalent circuit somewhat like this. This is R1, this is X1, and this is going to be R2 dash divided by S, and it is varying, and I'm going to have X2 dash, and I'm going to have this entire thing supplied with V1, and let me call this as either I1 or I2 dash. And I2 dash is going to be I2 multiplied by N2 divided by N1. Because we normally write V1 I1 equal to V2 I2 in a transformer, it is always valid. So I should be able to say V1 divided by V2 equal to I2 divided by I1, which is equal to N1 divided by N2. So I have essentially written, if I want to transfer I2 to the other side, this is how it should be. Based on whatever explanation I have given here, this is what is the expression. So, and one more thing we should remember is it is like a gear arrangement in mechanical system. With gear, you can reduce speed or increase speed, but correspondingly, if you reduce the speed, the torque would increase. If you try to increase the speed, the torque would decrease. But overall, the product of torque and omega power, that is going to be invariant. So across the transformer, across the gear arrangement, power is invariant on either side. Because of that, whether I write I2 square R2 or I2 dash square R2 dash, both are one and the same. It should not be a problem. So I can write mechanical power output for all three phases. That is going to be 3 I2 square R2 multiplied by 1 minus S divided by S. Right? Now, I can write this. This is going to be TE multiplied by omega R. That is electromagnetic torque generated multiplied by omega R. Earlier, we wrote omega S minus omega R divided by omega S is slip. So I should be able to write, that omega R, rather I should say omega S minus omega R equal to S times omega S, or 1 minus S times omega S equal to omega R. So let me substitute that in this equation. So I should be able to write 3I2 square R2 multiplied by 1 minus S divided by omega R equal to TE. And for omega R, I can substitute 1 minus S times omega S. So once I do that, I can write this as 3I2 square R2 divided by omega S. This is basically giving us, oh, I have left out S. So this S also has to be there. S times omega S. That is going to be our electromagnetic torque expression. And I can write this as 3I2 dash square R2 dash divided by S omega S. It doesn't make any difference whether I write I2 square R2 or I2 dash square R2 dash, where I2 dash is the current referred to the stator side and R2 dash is the rotor resistance referred to the stator side. Now we said I2 dash and I1 are one and the same as an approximation. So from this circuit, I should be able to write that I2 dash or I1, that should be equal to V1 divided by real part, that is R1 plus R2 dash divided by S plus J times X1 plus X2 dash. This is what is the current value. So I can also write this somewhat like this, that V1 divided by R1 plus R2 dash divided by S the whole square plus X1 plus X2 dash the whole square root of this. Okay, so this actually gives the current expression for the induction motor. So I can substitute this current expression what I have got in this place. So I should be able to write this as electromagnetic torque equal to 3 times V1 square divided by the square root of this. When you square it, you can remove the square root sign completely. So it will be R1 plus R2 dash divided by S the whole square plus X1 plus X2 dash the whole square. And here whatever is there, I have to write this as it is, S omega S, R2 dash divided by S omega S. So this is the electromagnetic torque expression that has been derived for the induction motor. So if I may look at two different situations. Let me first of all look at when omega R is close to 0. Under such a condition, omega s minus omega r divided by omega s, which is slip. Slip is close to 1. Slip is going to be close to 1. And if you look at induction motor winding, R1 is the resistance of stator winding, which is made up of either aluminum or copper. That is definitely going to be much low. R2 is either made up of, again, copper conductors. In the case of wound rotor, squirrel cage means it is going to have thick rotor bars. So the resistance is going to be really small. So R1 and R2 are very small or smaller, much smaller compared to X1 and X2 dash. That is the way it is going to be. So because of which I can say TE is equal to 3V1 square R2 dash divided by S omega S divided by X1 plus X2 dash the whole square, approximately. I can say that. In that case, I can say from here TE is proportional to 1 by S. If I assume that V1 is fairly a constant, R2 dash is fairly a constant, and X1 and X2 dash are also constant values. So, in this particular case, the electromagnetic torque with respect to slip, it is going to follow a hyperbola kind of configuration. Whereas, when I am looking at the other range, when omega r is close to omega s, when it is close to omega s, slip is close to 0. So when the slip is close to 0, under such a condition, R2 divided by S, if originally R2 is only 1 ohm and slip is 0.01, in that case, it is going to be increased by 100-fold. So if R2 is 1 ohm and slip is going to be 0.01, R2 dash divided by S is going to be 100. So it is increased multifold in that case. So I should say under such a condition, R2 dash by S, R2 dash divided by S is going to be much, much higher than R1. Also, it is going to be much, much higher than X1 plus X2 dash. Because even in an induction motor, leakage will be somewhat limited because it is made up of ferromagnetic core. So you would not see much of flux leaking away. So under such a condition, I can say electromagnetic torque is equal to 3V1 square R2 dash divided by S omega S. And I can say this can be neglected as well as R1 can be neglected. So it will be R2 divided by S the whole square. So I can write this approximately as 3V1 square S divided by R2 dash omega S. So I can say under such a condition, we are going to have TE is proportional to S. So there are specifically two regions what I have when slip is small. We are going to have TE proportional to slip. and when slip is close to 1, under such a condition, I'm going to have TE is proportional to 1 by slip. So we should be able to draw the characteristic somewhat like this. If I say that this is the slip I'm talking about, and this is going to be the torque, electromagnetic torque. So if I say this is synchronous speed, at synchronous speed, the torque has to be 0. Because if the rotor speed is same as synchronous speed, there is no induced EMF, there is no rotor current, there is no flux production from the rotor side. So there is no question of any torque production. So that is going to be, torque production is going to be 0. Under such a situation, slip here is 0, because when omega r equal to omega s, slip is 0, and slip is increasing from 0 to 1 in this direction. So this is slip equal to 1. And what we are plotting is on one side the slip which is increasing in this direction. If I say omega r is equal to omega s there, and omega r is equal to 0 here. So omega r is increasing in this direction. So when slip is small or it is close to 0, we are going to have a linear characteristics for torque. And when we are talking about slip is close to 1, we are going to have some kind of hyperbola. So this is going to essentially work like this. So when we have the intersection of these two, this is the point where we are going to have maximum torque. This is the maximum torque that the induction motor can deliver. So if you really draw the complete characteristics, you should draw something like this. It is going to be somewhat linear, and it is going to be like a hyperbola during this time. So this portion is proportional to 1 divided by slip, whereas this portion is proportional to slip itself. And this particular torque, that corresponds to the maximum torque that can be delivered by the induction motor. If you try to load the shaft beyond this value, the entire mechanism will break down and the induction motor will not be able to deliver the torque anymore. So this generally is also known as breakdown torque, TBD. So this is breakdown torque. That's what you would normally see as the breakdown torque. So if actually I have got the expression for the torque as 3v1 square r2 dash divided by s omega s divided by r1 plus r2 dash divided by s the whole square plus x1 plus x2 dash the whole square. The major changing parameter in this whole thing is only slip. All the other things are machine parameters. Whether it is stator resistance, rotor resistance, stator leakage reactance or rotor leakage reactance, all of them are machine constant. And if I am going to assume that it is working at 50 hertz and 440 volts or something like that, all these quantities are also constants. So under such a condition, if I say dTe divided by ds equal to 0, if I do that and then calculate what is S value, that will actually give me what is the slip at maximum torque, S max T. And if I substitute that S max T into this equation, I should be able to get what is T max or TBD. So this S max T you can calculate by doing this differentiation dTe divided by ds equal to 0, and that will give you the value of S max T as approximately R2 dash divided by R1 square plus X1 plus X2 dash the whole square root. If I assume that R1 is really small, I can also write this as R2 dash divided by X1 plus X2 dash approximately. So I can write this approximately as, R2 dash divided by X1 plus X2 dash. This is S max T. And if I substitute this value here, this will come out to be 3v1 square divided by x1 plus x2 dash multiplied by 2 omega s. Approximately this will be TE max, or this is the breakdown torque. So what you see normally in an induction motor is that it will be able to generate a maximum torque of TBD, and normally the slip of the induction motor, normal operating slip of the induction motor at rated condition or full load condition, it will be approximately 0.02 to 0.04. It will not be generally more than that. So you would see a very, very small drop in the speed. So almost this will be the point which may correspond to our full load condition. So the full load or rated speed is going to be only operating with 4% slip or 0.96 times omega s. That is going to be omega r rated. So under such a condition, it will be able to generate a torque. So let me call this as full load torque or rated torque. So normally in many of the cases, as a thumb rule, I can say TBD will be about 2.5 to 3.5 times T full load. Whatever is the rated torque of the induction motor, compared to that, it will be about 2.5 or 2 to 3.5 times. Generally, it is nothing more than that. So 2 to 3.5 times. And this poses a major problem in electric vehicles, because electric vehicles, especially starting torque, has to be quite high. And even sometimes for regenerative braking, or even in sometimes running condition, we might require a good amount of torque. In fact, starting torque, if you look at it in an induction motor, let me again look at this expression. When you are starting, slip is 1. When you are running, slip is going to be only 0.02, 0.03, something like that. So when you write this, TE during starting, that is going to be 3v1 square R2. Starting slip is 1. So I should write omega s. And I'm going to write R1 plus R2 dash the whole square plus X1 plus X2 dash the whole square. So this is what is going to give us the starting torque. And if you look at it, R1 is a very small value. So also is R2. And the same thing is going to happen for X1 and X2 dash. These are also small. And we already wrote the expression for the current somewhere. We said that when we write the current, right? The current expression, we wrote it like this. V1 divided by R1 plus R2 dash divided by S the whole square plus X1 plus X2 dash the whole square. And S is going to be 1 during starting. So I can write during starting, I'm going to have the starting current, that is going to be V1 divided by R1 plus R2 dash the whole square plus X1 plus X2 dash the whole square root. And because R1 is small, R2 dash is small, X1 is small, X2 dash is small, I2 starting is going to be really, really large. So this can be as high as 5 to 8 times I rated or I full load. So the current is going to be really large, but the starting torque will not commensurate with whatever is the starting current. What I mean is your starting current may be 5 times or 8 times, but the starting torque is not going to be 8 times the full load torque. There is no way. That is because this S is completely removed from this equation. Otherwise, S, if it is 0.01 or 0.02, that coming in the denominator would have increased the entire torque factor by 50 times or 25 times. But because S is 1, the starting torque is not going to be so high. Physically, if you want to really look at it, that although the current is high, the R2, what it is dissipating, most of it goes away in the real power. And there is real power dissipation, heat dissipation. Hardly anything is converted into mechanical power. Because if I look at the equivalent circuit and I say that R2 divided by S is the overall resistance visualized from the stator side, R2 dash divided by S minus R2 dash. This is what is really contributing towards mechanical power quantity. So, if I am saying that S itself is 1, then I'm hardly going to have any mechanical power quantity at all. So, that is one reason why the induction motors, it's very difficult to use it with electric vehicle, because you are going to see normally that T starting is going to be hardly 1 to 1.5 times T rated or T full load. So starting torque is not high, but the starting current is going to be enormously high, and it is not going to be able to haul the entire weight of the electric vehicle. That is one reason induction motors have not taken off, although Model S of Tesla car initially used induction motor. After that, they also stopped using induction motor for electric vehicles. So, in general, for high performance electric four-wheelers, although induction motor would have been an ideal candidate because of its ruggedness, its self-starting nature, and so on, it has not been extensively used at all for electric four-wheelers. We will look at the speed control of a three-phase induction motor in the next class. Then we will venture into synchronous motor drive.